Hey everybody, video number 3, types of energy. Let's differentiate between heat and temperature. Sorry, there's two of these guys, so let me redo it. You got to find space to write the other one in there somewhere. Here's the first one. I can distinguish between heat, energy, and temperature, which is a measurement. Okay, that's the first one. And there's another learning target. I can convert units of temperature using the temperature equation, table T. Okay, so get both of those in there somewhere. If you can fit them both in that box, great. If you can't, you'll find some room for them somewhere on the page. Okay, but please definitely write those down. And let's get right into it. So, two kinds of energy. Here we go. Kinetic energy. You see that bad boy? Everybody's moving around. Kinetic energy is, first of all, heat is energy that causes molecules to move. This is the energy of motion, kinetic energy. Kinetic energy includes three types of motion. First, translational motion. This is the one move from one location to another, moving classes. Okay, if you go from one class to another, that is what's called translational, and you've heard that when you went to translate over the x-axis or over the y-axis in math. Okay, and there is rotational motion. This is just spinning around on an axis, not moving any location A to B. Okay, and then there is something called vibrational motion, where I'm not even spinning. This is just the wobble back and forth without spinning. This is what happens in solids that are still technically moving because there is some latent heat involved. Okay, potential energy. This is a different kind of thing. This is the energy of position, but that's more of a physics definition. Okay, this is the energy of position or stored energy. For us, this relates to what we call phase change and energies stored within chemical bonds. So, chemical potential energy is stored within chemical bonds, and then physical potential energy is more in the phase changes of liquids, or I'm sorry, of any substance. So, as water goes from solid to liquid, there's a phase change, and the potential energy is what's changing during the phase change. When it goes from liquid to gas, we're going to learn the names of all the phase changes, and then that's where potential energy is either increasing or decreasing. And the nice part is that makes sense. If I'm heating, potential energy increases. If I'm cooling, potential energy decreases. So that part at least makes sense, and there's not a trick like there is in so many other things in chemistry. Um, all right, comparing and contrasting heat and temperature because they are not the same thing, but they are close. Number one, heat is kinetic energy. So heat is energy. Um, things technically, there really is no such thing as cold. And you'll get mad at me for saying that, but it's true. There's either heat or there isn't. There isn't a measure of no heat. The number for heat is just low. We don't have a number for cold. We don't measure how cold something is. We measure how much heat it has, and then that amount of heat might feel cold. Okay? So there's either heat or there isn't. Temperature is simply the measure of average kinetic energy. So temperature is the measure of heat. Okay? Units. So this is big. Joules, J. And you'll see that that's the units, J, but it actually, the variable is Q. Okay, but we measure it in units of measure. We measure Q in joules. Temperature we measure in one of two ways. We measure it either in Celsius, which is degrees Celsius, or kelvins, which is no degrees. We just call it kelvins. We don't say degree Kelvin. Okay, just say kelvins. I'll probably mix that up probably once or twice throughout the unit, and that's it because I'm pretty good at that. And I'll probably catch you guys a few times, and probably just say something, but you don't have to worry about it. It's not the end of the world, but it's just factually correct. Okay. Then here we go. Heat is dependent on mass. So this is a key overall concept. If you have two blocks of copper, one is 50 grams and one is 100 grams, and they're both at 50 degrees Celsius, well, the bigger one has more heat stored in it than the small one does because it's dependent on mass. So same temperature, different mass, different heat, because heat is dependent on the mass. I need to make sure we're all clear. Temperature is not. It's a direct measure, so it does not depend on mass. It just measures the temperature. Okay. We measure heat indirectly through changes in temperature. That's when we use that PBoM calorimeter. Okay, and that's how we measure heat. We basically burn it and see what happens to the change in the water temperature. Temperature, we measure that directly, not indirectly. We literally use a thermometer or a thermometer, you call it what you want, and that's what we use to measure the temperature, okay, directly. Heat flow, okay, there's three different kinds. So first one is conduction. When two objects at different temperatures come in contact with each other, the heat always goes from hot to cold until they equilibrate and they're at the same temperature. Once they're at the same temperature, heat flow stops. So it's a gradient thing. If you guys remember that word. Convection is when warmer areas of liquids or gases rise to cooler and then they form the cycle. So this is something I'm sure you studied in earth science. Guessing. Okay. And the last one is radiational. This is a method of heat transfer that does not really does not reply or rely on any contact. So this is like the sun. You can feel the sun's rays, and it's not a direct. The sun isn't directly touching anything. Okay, it's a form of radiomagnetic heat or thermal energy. So heat can be transmitted through empty space by thermal radiation. That's how the sun heats the earth. An example: 100-gram cube of ice at 0 degrees comes in contact with a 1,000-gram copper cube at 50 degrees. Which direction will the heat flow? Always from hot to cold. I can see what is the hotter thing. In this case, the mass does not have a play because the mass has to do with total energy or heat. Okay, so it's going to go from the copper cube to the ice cube. The copper cube is at 50 degrees. The ice cube is at 0 degrees. You know, it goes from the hot thing to the cold thing. So the correct answers here are from the copper to the ice, from 50 degrees to 100 degrees, from hot to cold. Never up and down, never left and right. Okay? Okay. Make sure we got that. Absolute zero theory. This is a good thing. So this is the temperature theoretically at which all motion stops. I say theoretical because we are not there yet. We are something like zero point 0.4 kelvins away. This scale, Kelvin, encompasses total energy. So it's not just limited to the melting point and boiling point of water. It considers total heat and total energy. That the vibrational energy, the rotational energy, and the translational energy. And if you get cold enough, translational energy stops, but it still might rotate and it still might vibrate. And then as we get even colder yet, it's just vibrate. And when all the vibration stops, that would be what we call absolute zero. So this is, by the way, this is 0K. It doesn't say that there, but absolute zero is 0 kelvins. Okay. Heat is energy. It is specifically kinetic energy. And then temperature is simply the measure of average kinetic energy. It seems like the third time I've said that, but I need to get those definitions ingrained in your brains because it can only go that way. Heat is energy, temperature is measure of average kinetic energy. So it's much like when I used to say protons are, and you guys would say king. I'm going to say heat is, and I'm going to expect you guys to say energy. Okay. Some quick conversions from Celsius to Kelvin and Kelvin to Celsius. This is the reference table in T. It's the bottom one in table T. And so you get this equation. So E is equation. There's my equation. I need to substitute in now that 98 degrees, put it there and make it look like this. So Kelvin would be 298 plus 273, which equals 371 kelvins. So those are the same temperatures. Okay. If I'm going to take 273K and convert it into Celsius, excuse me, sorry about that. I need to use the same equation. But now I don't think that you necessarily are happy with the fact that Kelvin would be plugged in on that other side and I have to manipulate it. So I would personally, I manipulate the equation first, rearrange to get Celsius by itself. We'd subtract 273 from both sides. And then I can simply just switch sides if I want, make Celsius on one side. So that's a little bit more plug and chug friendly. I can just take the 273 and plug it into that K, and I get 273 minus 273, which is 0 kelvins. I'm sorry, 0 Celsius. 0 Celsius is 273 kelvins. Total energy. Freezing point of water still has energy. Okay, frozen water, you might think that it has no energy. It does, because it's not at absolute zero. Absolute zero is when all energy is gone. So comparing Celsius to Kelvin, Kelvin and Celsius are on the same staircase, so to speak, and that's because the change in Celsius equals the change in Kelvin. And you could do that if you'd like. You could say um, 298, or you could go, what is the change here? And go pick two numbers, like 0 degrees Celsius and 100 degrees Celsius. And the difference there is 100. And then if you convert both of those into Kelvin, you see 0 Celsius is 273 kelvins, 100 Celsius is 373 kelvins, 273 and 373. The change is still 100. So they're on the same staircase. Okay. But the major difference is degrees Celsius is based on the freezing point and boiling point of water specifically, where Kelvin is based on total energy. So we'll use that in our heat equations because we can't ever have a temperature of 0 in Kelvin, and temperature is in the denominator of our equations. And you know what would happen if we put a 0 in the denominator of any fraction? Life would get crazy for us. So we're not going to go there. We use Kelvin specifically in P1 V1 over T1, where when we have change in temperature in one of the heat equations, you'll find that you can use the change in Kelvin or the change in Celsius, and it's the same number. So we don't have to go converting, okay? That's it. Mind blown. 3 videos down, 5 to go.